Okay, so hello everyone. My name is Youyang Wang. Today I will present my project for Module 1. The topic is predicting Abalone Age. So I will compare different modules and explain a key concept called the bias variance trade-off. First, what is a business problem? So abalones are valuable seafood and knowing their age is important for farming. But the traditional way is to find the age is difficult and you have to cut the shell and count the rings under the microscope. This is slow and it kills the abalone. So I want to predict the age using only physical measurements like weights and lengths, and this way we do not need to kill them. And I use dataset with over 4,000 samples. The target I want to predict is the number of rings. Okay, so now let's talk about the data preprocessing. And before I build the modules, I cleaned the data. First, I changed the sex column in the numbers so the computer can understand it. And I also checked for outliers, so data points looked unusual in using the Tukey rule. And when I see the heat map in the dataset and coding, I found something important. The features of learns, diameter, and the weight are very similar. So the colors are very dark. So this means they are telling the same story. In statistics, we call this monocollinearity. And finally, I split the data 80% for training and 20% for the testing. So I started by establishing a baseline using a multiple linear regression module. Often we assume that simple modules won't perform well in the complex biological data, but the results were surprising. The module achieved a MSE of 5.1. Looking at the coefficients, we can see the impact that the multicollinearity I mentioned earlier. Some weights are positive and others are negative as they fight for importance. However, despite this, module remained stable and provided a solid benchmark for prediction. Next, I wanted to see if a more complex module could be better. I trained a decision tree regressor. Decision trees are known for their ability to capture nonlinear relationships, so I expected it outperform the linear module. However, the results were opposite. The decision tree produced MSE of 8.61, and this is significantly worse than the linear module. In fact, the error increased it by over 60%. So why did a smarter module fail so badly? This brings us to the most important concept of this presentation, the bias variance trade-off. The failure of the decision tree is a classic case of high variance or overfitting because I used a single decision tree without limiting its dips. It tried to learn every single detail and noisy point in the dataset, training dataset, and it memorized the training set perfectly, but failed, failed, failed to generalize to the new test data. On the other hand, the linear regression module success because of the high bias but low variance. It made a rigid assumption that age is linearly related to size, even though this is a simplification of biological reality. This rigidity prevents the module from being confused by the noisy its data. In this specific case, so simplicity is one. To verify these findings, I also ran other modules including lasso regression and neural networks using k-fold cross validation. So cross validation is crucial because it ensures our result is not just luck based on how we split the data. As you can see, so even these modules like neural networkings perform the similarity to the linear regression and the lasso regression actually performed worse due overfitting, underfitting. So this comes at no free lunch theory. Complexity is doesn't guarantee the better accuracy. Okay, so to conclude, the multiple linear regression was a clear winner for this dataset with a lowest MSE of 5.1. From a business perspective, this means we can predict age of an abalone with an error margin of really 2.2 years. Well, this isn't a perfect, but it provides a viable, non-invasive estimation method for harvest. And for future work, I would recommend two things. So the first, we must move beyond single decision tree to ensemble method like random forest and or the XGBoost. And this method combine many trees to fix the high variance problem we saw today. And so the second point is the feature engineering is needed to resolve the multi-core linearity between the white and the learns variables. And thank you for your time. I'm happy to answer any question.